Hello everyone. So today we're going to continue on our discussion on matrix methods. So yesterday we did an example on solving a system of equations using matrices, and I showed you that basically you're required to do two things for each column, and you start from the column on the left, which is the first column, and work your way to the last column in your coefficient matrix. And since each column requires you to first get the 1, then get the rest of them to be 0, you basically only have to do 2 steps per column. And if you do it correctly, by the time you go through all of that, you should be able to complete your matrix into this form. Okay, so keep that in mind. If you're doing it and you are making more steps than you need, most likely you are not doing it correctly. Okay, and remember, what you want to do is to finish one column completely before you move on to second column. If you don't do that, you will wind up messing up the progress that you make, and that's the reason why it requires you to do more steps. Okay, so as I say, this is a good indication. 2 steps per column. One column to get the number 1 in the right spot, and the second step to get all the zeros in all the other spot. That will finish the column. Then you move on to the next column. So today what I want to talk about is a little bit more on using the matrix method. So when using the matrix method to solve a linear system, you need to transform the coefficient matrix into what we call the identity matrix, if possible, or as close to the identity matrix as possible. So this process has a name. This process is called reducing a matrix. And the end result of this process is what we call a reduced matrix form of the coefficient matrix. So here's is where students often make mistake because they don't know how to identify a matrix is being in the most reduced form. Obviously, if your matrix reduced to the identity matrix, then that would indicate that you are completely done. So that's not the issue here. If you can reduce any matrix into the identity matrix, then there won't be no problem because everyone can identify that, oh, this is the identity matrix. That means I'm done. The problem is when you cannot do that. See, when you cannot do that, you need to understand when your matrix is in its most reduced form. Why is it important? Because if your matrix is in its most reduced form, anything that you do will take it out of its most reduced form, meaning you just mess up your answer. Okay? Students often don't understand knowing when to start a process and also knowing when to stop a process is important. And some cases with this type of question, a student sometimes just doing the problem and not realizing that they are done with the problem. And so they continue to work on it, and meaning they just keep on messing up, bring it back, mess it up, bring it back, mess it up, and just keep doing it forever and over and ever. And that's when they run out of time. So make sure you understand. So how do I define if a matrix is in the most reduced form? Well, in order for me to define that, I do need to introduce two terminology. The first one is this one. The first the first non-zero entry in a row is often called the leading entry of that row. Important to understand is that the word leading entry is used to describe, is identified by a row. Okay? And it's the first non-zero entry. However, also important to understand is that any entry inside a matrix must be in both a row and a column at the same time. That is the reason why there are two subscripts under each entry. One to define the row that's in, and the one to define the column that's in. So we're using the column, meaning we look left and right. Left to right, the first non-zero number on each row become what we call the leading entry. Once we identify the leading entry, the column the leading entry is on also is important. The column that contains a leading entry is often referred to as the leading variable. So important to understand is that once you identify leading entries, you can also now identify what we call leading variable by identifying what columns they are in. But we don't use column to define leading entry. Leading entry is always defined by looking horizontally, looking along one row. That's why it's called leading entry of that row. Okay? What do I mean by that? Give you an example. Suppose I have this matrix right here. This is now the most reduced form. We'll call it a matrix R. R stands for reduced matrix. First thing I want to point out, notice that the third row are all zeros. Because the third row are all zero, now this third row is become what we call trivial, meaning it doesn't give us any information. Also, not to mention, that make it impossible for us to get a 1 in the third spot on the third row of the identity matrix. And so therefore, this matrix can no longer be turned into the identity matrix. Okay? Now, let's talk about leading entries. In this case, if you look at row 1 and row 2, so look left and right along row 1, notice that this is the first non-zero number. And we look row 2, this one is the first non-zero number. So both of these are what we call leading entries. One of them is leading entries for the first row. The other one is leading entries on the second row. Notice that the leading entry on the first row is also appear on the first columns. So column number 1, this column, contain a leading entry. Therefore, is referred to as a leading variable. And column number 2 also contain a oops. All right, there you go. Contain a leading, is also a leading variable also. Now, that will happen to the third column. The third column is often referred to as a non-leading variable. And what does it mean by non-leading variable? Well, we'll talk about it later on when we get to a different topic, okay? And we will talk about it most likely in later on in this section. We'll talk about what it is. It's called non-leading variable, okay? So in this case, because we have two leading entries, therefore we have two leading variable and leave one column to be called non-leading variable. Now, why do we call them leading variable? Because each column, remember, represent a variable, while each row represents an equation. So therefore, in this case, assuming that we have a system that go from x, y, z, then we are basically saying that variable x and variable y are what we call leading variable. And then variable z is called a non-leading variable. Now, what does that mean by leading variable and non-leading variable? We'll get to that in a little bit, okay? Now that you can identify leading entries and leading variable, now let's talk about what happened when a matrix is in most reduced form. A matrix is in its most reduced form. Meaning that once you reduce down to this form, nothing you can do to make it more reduced. Anything that you do would actually take it out of its most reduced form. Therefore, mess up your problem. A matrix in the most reduced form if it satisfies the following two conditions. Number one, if a row contains a leading entry, then that leading entry must be the number one. Okay, it cannot be any other number. If you have a leading entry, it must be number one. Now, then think about it. How could a row contain no leading entries? Simple. If it's all zero. If it's all zero, it contains no leading entries. Okay, so therefore, barring any row becomes zero, you should have the same number of leading entries as the number of rows in your matrix. Okay, so like this example right here, if you look at the matrix R, notice the matrix R 3 rows, but then the third row become all zero and therefore leave you with 2 leading entries. Okay, second condition 2. If a column contain a leading entry, meaning that if a column is a leading variable column, then other than the leading entries, which must be 1 by the way, the rest of the column must be all zeros. Okay? Those are the 2 conditions that a matrix must satisfy. Despite what it looks like, if it satisfies these 2 conditions, it is considered to be in its most reduced form. Even though it doesn't look like the identity matrix. That's the purpose of defining the reduced matrix using this definition. Is that for you to identify when a matrix doesn't look like it's the most reduced form, but actually it is. As a matter of fact, if you look at this matrix right here at the top, this matrix is in the most reduced form. Why? Let's see. We have 2 rows that contain leading entries. The third row does not. And both of the leading entry where I circle, they're both 1. So that satisfies the first condition. Now, second condition, column 1 contain a leading entry from the first row. The rest of the columns, 2 zeros. Very good. Second column contain a second leading entries in the second row. The rest of them are both zero. Therefore, now it satisfies both conditions. As a matter of fact, in the ideal scenario, you want the leading entries to be along the main diagonal. But please don't force it into it. In some cases, there will be example where that won't happen. Now, show you an example to illustrate this process. Okay, ready? So, give you a very simple example to illustrate, and also kind of show you what happened when you have something that cannot be reduced into the identity matrix. So suppose we have this equation right here. Okay, so let's say we're going to try to solve this. Okay, I'm just going to say solve. So first thing I'm going to do is let's go and put it into matrix form and see what happens. So this would be 1, -2, 1, 2. And we'll draw a line and put the right side matrix on this side. On bottom, notice there's no x and y. You have to put in 0 for placeholder. 1z, -1w, 1. Now, as a matter of fact, so here's my question. This matrix is almost in its most reduced form. Actually, only require one step to put into the reduced form. So I'm going to ask you to pause the video and try to think about it and try to see if you figure out what is the only place that mess up this matrix. That's why it's not in its most reduced form. So go ahead and pause the video for a little bit and then go and look at the answers. And then when you're done, unpause the video, okay? So now I'm going to continue. So hopefully that you have figured it out, and now you unpause the video and continue. So the only number that messes up this matrix, that's why it's not in most reduced form, is this number right here. See, notice that we have a leading entry on the first row. That's this number 1 right there in the front. And the rest of the column, which only have one more number in it, is 0. So that's done. We don't have a leading entry in the second column, because normally we want the second column to have a leading entry along row number 2. But row number 2 have a 0. And there's nothing you can do to change that. So now we move on to the third column. The third column for row number 2, it does have a 1. That means this is our leading entry. But third column in row 1 is also a 1. We need that to be 0. And that would complete row 3. Okay? So to do that, what we're going to do is this. Remember, to get 0, you combine. So in this case, I'm going to take row 1 at -1 row 2 and make that into my new row 1. So row 2 stays the same. Row 1, these two numbers stays the same. This number, the third number, becomes 0. The fourth number will be 2 plus -1 times -1. That gives you 3. And the last number is -1 plus 1 times -1, which becomes -2. Hard to believe, but this matrix is now in its most reduced form. This is our reduced matrix. Does it look like we're done? No, it does not. That's the problem. You have to learn to identify that you're done. This matrix, as it is right now, no matter what you do, you're only going to mess up the matrix. Now, what is the implication when you cannot get your coefficient matrix to turn into an identity matrix? When that happens, usually what does it indicate is that you will have what we call an infinite solution system. So it's a consistent system where the solution will be infinite. So the question would be, how do we identify, or how do we represent infinite solution? Okay, so that's become the biggest problem. How do I represent the infinite solution? So to do that, you have to learn how to take this reduced matrix in its whatever its form and turn it into a solution set. So first, whenever you try to represent infinite solution in a linear system like this, you always represent your infinite solution in parametric representation. And in order to form it in parametric representation, what you need to do is identify parameters. And this is how you do it. If I look at my reduced matrix, here and here, these are my leading entries. That identify column number 1 and column number 3. Both of these. Let's see. There you go. So column, oop. Okay, maybe I'll fix this. Oops. There you go. Okay. And I'm going to get rid of this little thing. So that identify column number 1 and number 3 to be our leading variables. So in this case, what would be our leading variable? That would be x and z, because x is the first column, z is the third column. Then what do we do with 2 and 4, column 2 and 4? These two are now referred to as non-leading variable. So what do we do with the non-leading variable, which in this case are the y and the w? They become the parameters. So that would be how we go set up our solution. We go use x and y as a leading variable, and we're going to use y and w as a parameter. So how do we do that now? Very important, this process. Okay? What I'm going to do is rewrite this back into equation form. And we'll line them up. So that will be now my equivalent system. Okay? First thing you want to do is solve for the leading variable. Each leading variable can only appear in one equation. If that is not the case, you make a mistake. Something worth writing down, or remember, if you can think, you can remember it. But I would say write it down. Each leading variable can only appear in one equation. So if that's not the case, your matrix is incorrect. So my first equation have the leading variable x. So I'm going to go and write that as x equal to 2y minus 3w minus 2. My second equation, I'm going to do the leading variable z. Z equal to, line things up, w plus 1. Here comes the important step. What I want to do now is to set up my parameter. I'm going to go ahead and let y equal to parameter t1, w equal parameter t2. Now here's where students make mistake. Okay, student would say, oh, that would mean that this y right here is t1 and this w here is t2. So therefore, don't write this down because this is wrong. They say, oh, don't xz would equal to 2 t1 minus 3 t2 minus 2, and then t2 plus 1. So therefore, combine into this. Oops. Let's see if I have room to squeeze in. So that's my answer, right? Wrong. Why is it wrong? Seems like that's exactly what we're supposed to do. It's wrong because it's not in the right dimension. That's the reason. See, if you look at our problem, how many variables do you see? 1, 2, 3, 4. X, Y, Z, W. This entire system exists in R4. Therefore, whatever solution that we get should be in R4. But what you wrote here is in R2. That cannot be the solution because it's not in the right dimension. Very common mistake every year. Ton of students make that. The reason why they make that because they don't pay attention to what dimension they're working with. That's the problem. You have to learn to pay attention to that. More so as soon as we start calculus. If you don't pay attention to what dimension you're working with, you always will get confused. You always will get something wrong because you don't know what's going on. Don't do that to yourself. So what should you do? You do this. The problem, is you didn't line up everything. X is 2t1 plus negative 3t2 plus negative 2. I'm going to put plus instead of minus. That way I can group the number together correctly. What usually go after x? Well, it's not z, it's y. Y equal to t1. Then is z. Z equal to t2 plus 1. Notice I put the t2 line up with the t2. And then what go after z? W. W is t2. Now, once again, we'll fill in all the missing stuff so they can see how the vector come about. And now I can group all these numbers together. They would now form the vector that I need. When you group all these numbers together to form the vector, you have to make sure that it's all plus outside. If any one of them minus, the minus have to go inside the vector. So now I'm ready to write out my answer. In this case, we have vector x. Our vector x in this case represent x, y, z, w. Why? Because it's in R4. Is equal to T1, 2, 1, 0, 0, plus T2, negative 3, 0, 1, 1, plus negative 2, 0, 1, 0. Interesting thing to note, you should recognize this parametric expression because you learned it in chapter 1.3. If you don't remember what that is, go back to 1.3 and look. Okay? Show you. Right here. T1 vector U1 plus T2 vector U2 plus vector V. That is exactly what we have here. We have T1, we have this, which is vector X. Equal to T1. This is our vector U1 plus T2. This is our vector U2 plus this is our vector V. What we have here is a parametric representation of a plane. But this plane exists in R4. As a matter of fact, every time when you solve a linear system where its solution become infinite, it will always form some kind of plane like this one. The only problem is, remember, this is called the parametric representative plane because they have two parameters with two direction vector. So now comes the big question. What if you have more than two? Well, if it's more than two, then it forms something a little different. So I want to show you what that is. And this is basically talk about what we call the geometry of the solution set of a linear system. So the solution set of a linear system is always in the form of vector x equal to T1 vector U1 plus T2 vector U2 plus dot 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 plus T sub k vector U sub k plus vector V. Okay? This solution, we assume that this solution will be in some kind of Rn. And to be proper, n must be greater than or equal to k. So like in this case, this example right here, this is definitely in this form in R4. 4. And this scenario, this expression right here, we'll say k equal to 2 because we have two terms. So the k defines how many number of direction vector that you have, and then v is the position vector, technically speaking. And we do expect the number of direction vector for this solution set would be less than or at most equal to n. Very likely it would just be less than, as a matter of fact. This expression form what we call this parametric representation. Form what we call a k-plane in Rn. So the number k indicates the number of direction vector. Okay? So what does it mean is the following, meaning that a k-plane must have k direction vectors. And one single position vector in the parametric representation. So the direction vectors in this case are u1, u2, ... to uk. And the single position vector is vector v. All right? Because of the fact that it has k direction vector, a k-plane must also have k parameters. Now, interesting thing to note, and that will probably be the last thing I'm going to talk about because it's already past 30 minutes. Note the following. Notice that a line has this parametric representation. Oops, no subscript is needed in this case. That indicates k is equal to 1. Because I only have one direction vector, one parameter. Therefore, mathematically speaking, I can refer to a line as a one plane. Notice a plane that we learned in 1.3 is this thing. That tells me that k is equal to 2. Therefore, this is better referred to as a two-plane. And now this method continue. If you have an expression that looks something like this. Then that's k equal to 3. That's called a three-planes. Is that similar to a three-dimensional solid in R3? Maybe, maybe not. We don't know because we don't know how fourth dimension look like. Because in order for it to be a proper three-plane, it will have to exist in R4. So therefore, one plane exists in R2, while two plane exists in R2 and R3. Or actually, maybe I should write it this way. In R2 or higher. And a two-plane should exist in R3 or higher. And then a three-plane should exist in R4 or higher. And so on and so forth. Okay? So important to understand that these are all use the word plane, but they actually have different dimension. With that being said, we will talk about a line instead of using one plane. We'll talk about plane instead of two planes. But anything beyond two planes, we will indicate the dimension by giving the number in front. So therefore, we actually will be line, plane, and then 3-plane, 4-plane, 5-plane, 6-planes, and on. All right, unfortunately, that's all the time I got. So we're going to have to talk a little bit more about it on tomorrow's video. All right, talk to you guys later. Bye bye.